In this video, we're going to put some things together and talk about scores and probability. We're going to talk about probability's relationship to the DSM, also z-score's relationships to the DSM. You're going to need your unit normal table, so make sure that you have it at the ready. So the DSM tends to be normal, and therefore z-scores and the unit normal table can be used to find probabilities for specific sample means. So we can find probabilities for samples, and this is the basis for inferential statistics. Statistical inference uses sample statistics to make conclusions about a population parameter. So let's see what this means. First of all, we're going to change our z-score formula for individual scores to be a z-score formula that we're going to use for sample means within the DSM. And so we can take a look and see that the z-score is equal to the mean of the sample minus the population mean divided by the standard error. So whereas we had z equals the score minus the mean divided by the standard deviation when we're talking about individual scores, we have it changed now to this new formula. So the purpose of the distribution of sample means, the reason why we even care about it, is because it can tell us the probability associated with finding a sample with a particular mean within the population. And standard error is essential for this process. So we're going to do a couple different learning checks. We're going to work this out to see what it looks like. We have a normal population with a mean of 80 and a standard deviation of 12. We're going to use the new z-score formula for sample means to find the z-score for the following sample mean. The mean is 84 and the n of the sample is 9. So let's take a look. So we have everything on this board that is needed to answer this question. So first I have the formula for z-scores when we're dealing with means as opposed to individual scores. It's the mean of the sample minus the mean of the population divided by the standard error. So the standard error has its own formula here, the standard deviation divided by the square root of n. So we'll take this step by step. First of all, we know the population mean is 80, the population standard deviation is 12, and there are 9 people in the sample. And so we're looking at a mean of 84, and we want to find out where this mean of 84 would fit in a normal curve using a z-score. So we're going to take the mean of 84 minus the mean of 80, which is the population mean. So we have our sample mean minus our population mean. And now we're going to need to divide it by the standard error. So let's get that standard error first. It's the standard deviation of 12 divided by the square root of n. Square root of 9 is 3. 3 goes into 12 4 times. So we have 84 minus 80 is 4 divided by 4. So our z-score for this mean is 1.00. So let's take a look and see where this mean would fall. So I have the normal curve here, and I have a z-score of a positive 1. So I just come here, and that is where our mean of 84 would be found for our sample. So if we think about extreme samples, I'm going to color in the areas beyond -2 and +2, and I'm going to consider those really extreme. So if we were to take the distribution of sample means and we plot them all out, would it be very unusual to find a mean of 84? Well, not really, because we consider everything in the center part a high probability event. And so we basically are saying that 84 is really the same as the mean of 80. It's just we got 84 because of sampling error. Nothing's really happening here. This belongs to this population, in other words. Here's our next learning check. We have a normal population with a mean of 80 and a standard deviation of 12. We're going to find the z-score for the following sample mean with an m of 74, a mean of 74, and an n of 16. Let's do it. So once again, we have everything that we need here. We have the formula for z for means, the standard error of the mean. We have the population mean of 80, standard deviation of 12. This time we have an n of 16 and an a mean for our sample of 74. We're trying to figure out where this mean of 74 would be in the distribution of sample means for this population. So what we're going to do first is we're going to find the mean of 74 minus the population mean of 80. We've done that. And then the next step is to do the standard error of the mean. So we can come over here and do that. We have a standard deviation of 12, and the square root of n is the square root of 16, which is 4. So our standard error is 4 goes into 12, which is 3. So now we're ready to find our z-score for a mean of 74. We have 74 minus 80 is a negative 6 divided by 3. 3 goes into negative 6, negative 2 times. So our z-score for a mean of 74 in the distribution of sample means is going to be a negative 2. Let's see what that looks like on the distribution. So we have the distribution of sample means written out here, this normal distribution. We have a z of negative 2, so I'm going to put it right here. And if you'll notice, we're starting to get really close to these extreme areas with a negative 2. Anything beyond negative 2, we're going to be calling extreme in this case. And so what we're saying is a mean of 74 is pretty unlikely to be obtained in that distribution of sample means. Most of the means cluster very close to the mean of 80. But when you start to get really far out here, we start to wonder if maybe it's not just a matter of sampling error that we're dealing with, but maybe my mean of 74 is somehow really different than this population. Maybe this group that got a mean of 74 is very different from the population that we thought it came from. So maybe this mean of 74 comes from a different population. Okay, let's try another. Here's another learning check. A normal population has a mean of 80 and a standard deviation of 12. Find the z-score for the following sample mean. The mean is 81 and the n of the sample is 36. Okay, we have everything that we need. I won't even go over it again, but the only thing that's different is our n is 36 in this case, and the sample mean that we're trying to figure out where it belongs on the distribution of sample means is 81. So I'm going to first use my z formula, 81 minus the mean of 80. I already know that that's going to be pretty close. Those are pretty close, aren't they? Let's figure out what that standard error is going to be. We have a standard deviation of 12 divided by the square root of 36, which is 6. 6 goes into 12 two times. You'll notice that as our sample sizes are getting bigger, our error is getting smaller. Okay, 81 minus 80 is 1 divided by 2 gives us a z-score of 0.50. We could say a positive 0.50. Let's see where this is in the normal distribution. Okay, so it is a half of a standard deviation basically. A z-score of 0.5 is halfway between 0 and 1. So I'm going to draw the line right here. And this is going to be where our mean of 81 would be. And so again, when we think about the extreme areas, 81 is pretty close to 80. So I'm more likely to say that, yes, 81 is a little bit higher than 80, but this is just sampling error. And they really, if you were to look at the whole population, our mean would be 80. But we drew a quirky sample, it's 81, but it's not really different from this 80 is what we're saying. Every sample mean has a z-score that describes its position within the distribution of sample means. This makes it possible to use the unit normal table to find probability associated with sample means. Just like we used it to find probability of finding individual scores, now we're going to use it to find the probability of finding certain sample means. We're going to make predictions with these probabilities and proportions. Let's do a learning check to see what this looks like. We have a random sample of 25 scores, and that's selected from a normal population with a mean of 90 and a standard deviation of 10. What is the probability that the sample mean will have a value greater than 94? So let's work this out. The first step in solving this problem is going to be to find the z-score for a mean of 94. We need to do that first before we can figure out the probability of finding a mean greater than 94. We need to find the z-score boundary, in other words. So let's do that. Let's find the z-score. We have, first of all, we had a mean of 90 in the population, standard deviation of 10, and our sample size is 25. So let's find the z-score first. We're going to take 94 minus 90, which is our population mean. We're going to divide it by the standard error, so let's figure out what that is. The standard deviation is 10 divided by the square root of n. Square root of 25 is 5. So our standard error is 2. So we have 94 minus 90, which is 4, divided by 2. So our z in this case is equal to a positive 2.00. So let's take a look and see what column we're going to be looking at the unit normal table. We figured our z-score was a positive 2.0, and we're looking for all scores that are greater than a 2.0. So this is the shaded area that we're going to be looking at. So look at your unit normal table and see if this shaded area reminds you of column B, C, or D. Okay, I have some areas of the unit normal table here to help us out. So first of all, I have the illustrations. So were we looking for something that looks like column B or column C or column D? Well, we shaded in the tail area, so we're going to be looking in column C. Now, if you will recall, our mean of 94 had a z-score of 2. So I'm going to come to the Z column, I'm going to find 2, and then I'm going to look in column C, the proportion in the tail. And I see that it's 0.0228, which we can translate to say 2.28% of the scores are above a z-score of 2, or you can say 2.28% of the scores are above 94, which was our mean, which we found at positive 2. So there you go, 2.28% or 0.0228 is the answer. Here's another one. A random sample of 25 scores is selected from a normal population with a mean of 90 and a standard deviation of 10. What is the probability that the sample mean will have a value less than 91? Now you pause the computer and try this on your own first. So again, we still have the same population mean, population standard deviation, and n of 25, but this time our mean is 91, and we're going to find out the probability of selecting a score that is less than 91. So what we're going to do is we first have to figure out what is the z-score at 91. So let's take a look. So we have our score of 91 minus the mean of 90. We need to divide it by the standard error. Standard error is the standard deviation divided by the square root of n. So the square root of 25 is 5. Our standard error is 2. So 91 minus 90 is 1 divided by 2. So our z-score for 91 in this case is a positive 0.50. So let's look at the unit normal table to see what percent are going to be below positive 0.50. But before we do that, so 0.50 would be here, and we're looking for everything under a 0.50. So one clue as to what column we're going to be using on the unit normal table is we're crossing the body. When we're crossing the mean over, that's called crossing the body. So let's look at the table. So we're looking for all of the values below a z-score of positive 0.5. In other words, all the values below our mean of 91. So as I just illustrated, we're really looking at the body in this case because a z of positive 0.5 is here, and we're looking for all of the scores that are less than. So we're going across the body. So we're going to be looking at column B for a z-score of 0.5, which I have right here. And it looks like the proportion in the body is 0.6915, which means that 69.15% of the scores are below a z-score of 0.5, or you can say 69.15% of the scores are below 91, that raw score. All right, here's one more. A random sample of 4 scores is selected from a positively skewed distribution with a mean of 60 and a standard deviation of 8. What is the probability of obtaining a sample mean greater than mean equals 62? Okay, I'm not even going to have you do this. It's a trick question. We can't use this on a skewed distribution with a small n. So we need to think about the criteria that needs to be met. Either the sample needs to come from a population that's normally distributed, or the sample size needs to be larger than 30. And this sample size was, first of all, from a skewed distribution population, and the sample size was only 4. So we didn't meet either of the criteria, and we cannot use the unit normal table on this distribution. And that's it for this video. And in the last video, we're going to walk through a scenario where we put all of this together.